Hi, in this video we will learn what is a linear transformation. We'll do some examples also, checking if some transformations are linear or not. Let us start with the definition of a transformation. So a transformation T from Rn, so let me write T here, from some Rm to Rn, they may have different dimensions, is a map, a function from Rm to Rn. What does it mean? It means that, well, for any vector v, so vector v with m components, these are all, this form Rm, yes? This sense for any vector like that, something unique in Rn, which we denote as a vector, unique vector, TV in Rn with n components. Okay, this is the definition of function. And usually in practice, what we do is we write down the components of TV in terms of components of V. Let's do some examples. For example, we have T going from R3 to R3 to R2, which does this thing, that T add a vector with 3 components, it takes it and it sends it to something with 2 components, like x plus y, then minus 1, 3y minus z. Well, what does this mean? It means that you plug in everything you like here. For example, vector 1, negative 1, 2. Then the result will be a new vector which has 2 components. And how do you find the components? For the first component, you add first component and second component of this guy and subtract 1 from that. For the other one, 3 times negative 1 minus 2. And this is basically what? Negative 1, and that will give us negative 5. Or you can go from, for example, R2 to R2. Something like, well, x, y, and then gives us, let's say, x squared minus y squared, or minus y, just like that. And, well, you can plug in values. For example, t of 1 and negative 1, this is going to be 1 squared. X squared will be the first component, minus negative 1, so this will be 1 and 1. 2 things that you need to know. Let me write it as notation or terminology. Well, T at V is called the image of vector V, this is vector V, under the transformation T. So in other words, here you see that the image 1, 1 is the image of 1, negative 1 under this transformation T that we have here also. Another notation we call the set of all images of vectors under T is called the range of T. So you put all these vectors that T maps there, put them all together, that will form a set. We call it image of, range of T. Okay, so this is just general transformation, but what we are interested in, what we will study in details is what is called a linear transformation. Linear transformation. T going from, again, some Rm to Rn is called is transformation which satisfies one. Well, if you try to find image of a vector after you scalar multiply it by c, so c is a scalar, any real number, then that will give you the same thing as T acts on a V, so it gives you the image of V, then you scalar multiply. And the second condition is that if you add two vectors and find the image under T, that would be equal to sum of TV and TW. So in other words, if it respects scalar multiplication and it respects vector addition. So it preserves the structure of vector spaces. When you multiply some vector by scalar, the image of that vector is going to be multiplied by that scalar, and if you add two vectors, find the image, it will be the same thing as sum of the image of those vectors. Let's see some examples here. Very nice. Check if the given transformation is a linear transformation. Okay, nice. So we have these guys here. So this, as you see, goes from R3 to R2. And is it a linear transformation? For that, I need to check two things. First thing is that if I multiply a vector, the vector x, y, z, by a constant, what do I get? This is going to be, I know how the scalar multiplication works, yes. Now, T of Cx, you see the first component is now Cx, and what does T do? It adds the first component to second component, so it will add Cx, Cy, then minus 1, and here 3Cy minus Cz, the third component. Well, that is T of Cxyz. How about C of Txyz? Well, let's see. T of xyz is x plus y minus 1, 3y minus z, yes? Then you multiply that c in, scalar multiply, this will be c times x plus y minus 1, and c times 3y minus z. As you can see, this is going to be cx plus cy minus c, and 3cy minus cz. Now, the question is, are these two guys equal or not? Because that's the condition we have to check. Well, let's go check one by one. The second component is exactly what we are expecting to have. But the first component is cx plus cy minus 1. Is it equal to cx plus cy minus c for all scalar c? Well, as you can see, this cancels with that, this cancels with that. And as you see, no, not for all c. This doesn't happen. This needs to be true for all c's, but this is not true for all c's. So that right away means that the first condition that fails the first condition. Actually, you can check that this transformation does not satisfy the second condition too. It doesn't send vector addition to vector addition. Okay, so this is not a linear transformation. How about this other one? Okay, let me just make a bit of space here. How about this one? TV is T at V. Image of V under the transformation T is equal to inner product of 1, 2, 3 and V. By the way, this V comes from R3 and T basically picks something in R3, and what it gives us is a number, so it goes to R. Okay, now, is it a linear transformation? First thing to check is, does it preserve the scalar multiplication? So here, T of C, X, Y, Z. This is going to be T of Cx, Cy, and Cz. And this is equal to what? Here this says 1, 2, 3 dot C, X, Cy, Cz. Well, we can do this work, and we can see that this is going to be 1 times Cx plus 2 times Cy and plus 3 times Cz. But that means that I can factor out C. This is 1 times X plus 2 times Y plus 3 times Z, which is exactly the inner product of 1, 2, 3 and X, Y, Z. And this is what? This part is TV, and that C is scalar multiply. Well, actually, I could have done better work if I just do use the properties of dot product. Let me call this guy as W. W dot CV. We know that the inner product and scalar multiplication work nicely together. So this will give us this, which is equal to CT of V. Yes, it preserves scalar multiplication. How about the vector addition? So T of V plus U, this is W dot V plus U. And this is what? W dot V plus W dot U. The first one is exactly T at V, and the second one is T at U. And as you can see, T of V plus U is equal to TV plus TU. So that means that, yes, this is a linear transformation. We have to check both conditions, and that gives us what we have. Let's check this other one. Here we go from R2 to R2, and we have to check the first one. Let me check the, well, Sure, the first one is good one. T of cxy is T of cx cy. And then what does this formula says is that pick the first component and square it. So here we get cx squared. And the second component you multiply it by y. And as you can see, this is c squared x squared and then c times minus y. And well, if you look at c scalar multiplied to t of xy, what we get is c of x squared minus y, but when you scalar multiply, you get cx squared minus cy. What you see here is that the question is that are these equal or not? Yes. The second components, yes, these are okay. But when you look at the first component here has c squared multiplied to the first component. But here, it only c is multiplied by x squared. So it means what? It means that, for example, if you t of 2, 1, 1 is not going to be equal to 2 of 1, 1. Sorry, 2 of t of 1, 1. And well, the answer for this question mark is no, so this is not linear. And let's check the last one here. So here I have R2. Then for any vector in R2, this assigns a vector. Well, this is a number. Well, or vector in R, a number. And we have to check scalar multiplication. T of cxy is equal to T of cx cy, which is cx. This says what? Add first component to negative 2 times second component. The first component is cx minus 2 times cy. And this you can factor out c, you get 2y. And as you can see, this is t at x, y. So it preserves scalar multiplication. How about vector addition? So t of uv, let me write, instead of uv, write x1 y1 plus x2 y2. This gives us x1 plus x2 and y1 plus y2. And what is this? This is the first component, which is x1 plus x2, minus 2 times the second component. But while we can separate these things and write x1 minus 2y1 plus x2 times minus 2y2. This guy here is t of x1 y1 plus t of x2 y2. And this sends vector addition to vector addition. And that means that after checking these two conditions, yes, it is a linear transformation. Let me finish this video with two remarks. Remark one is that, okay, so what does this guy, if t is linear, then what does it do with the linear combination? So if you have t of c v1 v1 plus c2 v2, first of all, we can see that this guy I can see as addition of two vectors. So for linear, we can separate these guys. And then each one is scalar multiplication. So this one gives us c1 t1 plus c2 t v2. And well, what this says is that it sends a linear combination to linear combination. And if we take C1 and C2 equal to 1, sending linear combination to linear combination means that V1 plus V2 is equal to T of V1 plus T of V2. And if you take C1, let's say C1 equal to C and C2 equal to 0, then what this shows is that T of CV1 plus 0 equals to CTV1. Well, what I just showed you is that the condition that a transformation sends a linear combination to linear combination is equivalent to T being linear transformation. So let me write it here. T from Rm to Rn is a linear transformation if and only if T of CV1 plus C2V2 is equal to C of TV1 plus C2 of TV2. It sends linear combination to linear combination. So that's another way of checking if a transformation is linear or not. The second remark is that this is interesting fact to know. Remark 2. For a linear transformation, T going from Rm to Rn, we can see that T of the 0 vector is equal to 0 vector. Well, the first 0 vector is coming from Rm. The second 0 vector is coming from Rn. So it has m component. So it sends 0 to 0. Why is that? Because, well, if I take C equal to 0, C 0 times any vector is going to be 0 times T of that vector. But C of 0 times V is V, and 0 times TV is 0. So that means that linear transformation send 0 vector to 0 vector also. That's just something that you can use in some questions like this one. You see, in this problem here, if you take the T of 0 vector, it will give us a -1, 0, which is not 0 vector. So that's how we can say that this is not linear transformation, at least in some easy cases. Okay, so this was an introduction to linear transformation. We will learn more about it and more examples of linear transformation.